In the vast expanse of our universe, there exists an object so extraordinary that it challenges our understanding of cosmic brilliance. Picture, if you will, a celestial beacon so intense that it could outshine 1,000,000,000,000 suns like our own, a force of nature so magnificent that its radiance traverses billions of light years before reaching our telescopes here on Earth. These cosmic lighthouses are known as quasars, and they stand as the brightest known objects in our entire universe. When we gaze into the night sky, we see countless stars, nebulae and galaxies, each telling its own story of cosmic evolution. But quasars exist in a league of their own. They are nature's ultimate power plants, cosmic engines operating at the very edge of physical possibility. Their brilliance is so extreme that when astronomers first discovered them, they could hardly believe what they were seeing. How could a single object produce more light than an entire galaxy of stars? The light from these cosmic beacons has journeyed through space and time, crossing unimaginable distances to reach our sophisticated telescopes. Some of this light has been traveling for over 13 billion years, making quasars not just objects of extreme brightness, but also windows into the early universe. They serve as cosmic time capsules, allowing us to peer back almost to the dawn of time itself, when the universe was still in its infancy. Today we embark on an extraordinary journey to unravel the enigma of these celestial powerhouses. We'll explore the mysterious mechanisms that allow quasars to generate such phenomenal amounts of energy, discover their crucial role in shaping the evolution of galaxies, and understand how these cosmic giants have helped revolutionize our understanding of the universe's fundamental laws. Before we dive deeper into this cosmic adventure through the extreme universe, I invite you to join our community of astronomy enthusiasts at Exploring the Universe. By subscribing to our channel, you'll ensure you never miss any content about the fascinating world of astronomy. Together, we'll continue to explore the most remarkable phenomena our universe has to offer, from the mysterious depths of black holes to the brilliant beacons of quasars that light our way through the cosmic darkness. These celestial objects represent more than just astronomical curiosities. They are cosmic laboratories where the laws of physics are pushed to their absolute limits. Through understanding quasars, we gain invaluable insights into the fundamental nature of our universe, the evolution of galaxies, and the cosmic forces that have shaped our reality over billions of years. Let's begin our journey into understanding these fascinating cosmic lighthouses that continue to captivate astronomers and inspire wonder in all who study them. When we first encounter the term quasar, we're dealing with a shortened version of quasi-stellar object, or QSO. This name emerged because when first observed through telescopes, these objects appeared to be stars, small points of incredibly intense light. However, the reality of quasars is far more extraordinary than anyone could have initially imagined. A quasar is actually the incredibly bright core of a distant galaxy, powered by a supermassive black hole that's actively consuming surrounding matter. To truly grasp the astonishing brightness of quasars, let's put their luminosity into perspective. While our sun appears brilliantly bright to us here on Earth, it pales in comparison to a quasar's output. A typical quasar shines with the brightness of hundreds or even thousands of entire galaxies combined. Imagine the combined light of 1,000,000,000,000 suns. That's the kind of energy we're talking about. If a quasar were located at the distance of Sirius, our night sky's brightest star, it would outshine our moon by a factor of millions and be visible even in broad daylight. The secret behind this extraordinary brightness lies in one of the most efficient energy conversion processes known in the universe. At the heart of every quasar sits a supermassive black hole, typically hundreds of millions to billions of times more massive than our sun. As matter falls toward this cosmic giant, it forms a rapidly spinning disk called an accretion disk. The material in this disk becomes superheated due to intense friction and compression, reaching temperatures of millions of degrees. This process converts about 10% of the infalling matter's mass directly into energy, far more efficient than nuclear fusion in stars, which converts only about 0.7% of mass into energy. When astronomers first detected these objects in the 1960s, their extreme brightness posed a significant scientific challenge. The sheer amount of energy being produced seemed to defy the laws of physics as understood at the time. How could an object that appeared so small produce such an enormous amount of energy? This puzzle led to one of the most significant astronomical debates of the 20th century. The challenge became even more perplexing when astronomers measured the spectra of quasars and discovered they were incredibly distant, billions of light years away. This meant that the actual power output had to be even more enormous than initially calculated, as the light we observe has been traveling for billions of years and has been significantly dimmed by its journey through space. The fact that we can see them at all from such vast distances is a testament to their incredible luminosity. Another fascinating aspect of quasars is their variability. Unlike most cosmic objects that maintain relatively stable brightness levels, quasars can change their brightness significantly over periods as short as a few days or even hours. This rapid variability provides crucial information about their size, as no object can change its brightness faster than the time it takes light to travel across it. This led astronomers to conclude that the primary energy-producing region of a quasar must be incredibly compact, smaller than our solar system, yet producing more energy than entire galaxies. The extreme brightness of quasars also serves an important scientific purpose. They act as cosmic beacons, allowing astronomers to study the material between them and Earth. As their light travels through space, it passes through countless clouds of gas and dust, leaving telltale absorption signatures in their spectra. This has helped astronomers map the distribution and composition of matter throughout the universe, making quasars invaluable tools in understanding cosmic structure and evolution. Understanding quasars and their extreme brightness continues to push the boundaries of our knowledge in physics and astronomy. These cosmic powerhouses represent some of the most energetic and efficient processes in the universe, and their study has revolutionized our understanding of black holes, galaxy evolution, and the fundamental laws that govern our cosmos. The discovery of quasars stands as one of the most revolutionary moments in the history of astronomy, marking a turning point in our understanding of the cosmos. The story begins in 1963, when Dutch astronomer Maarten Schmidt made a breakthrough that would forever change our view of the universe while studying a peculiar object known as 3C273. The journey to this discovery began when radio astronomers had identified several mysterious sources of intense radio emissions that appeared star-like when observed with optical telescopes. 3C273, located in the constellation Virgo, was particularly puzzling. Through the optical telescope at Palomar Observatory, it appeared as an unusually bright blue star with a faint jet-like appendage. But its spectrum made no sense when interpreted using conventional stellar analysis. Schmidt's eureka moment came when he realized that the mysterious spectral lines he was observing in 3C273 were actually familiar hydrogen emission lines, but dramatically shifted toward the red end of the spectrum. This redshift was far more extreme than anything previously observed in any celestial object. Using the Doppler effect principle, Schmidt calculated that 3C273 was receding from Earth at the incredible speed of 30,000 kilometers per second, placing it at a distance of about 2.5 billion light-years from Earth. This revelation was staggering. If 3C273 was truly that distant, its apparent brightness meant it had to be hundreds of times more luminous than an entire galaxy of hundreds of billions of stars. No known physical process could explain such enormous energy output from what appeared to be a relatively small object. The discovery sent shockwaves through the astronomical community. Following Schmidt's breakthrough, Astronomers quickly identified many more such objects, which came to be known as quasi-stellar objects, or quasars. Each discovery added to the growing evidence that these objects represented an entirely new class of astronomical phenomena. The spectral analysis revealed not only their extreme distances, but also provided crucial information about their physical properties, showing they were incredibly hot and surrounded by rapidly moving gas. The debate about the origin of quasars was intense and lasted for several years. Some astronomers initially suggested they might be nearby objects ejected from our galaxy at relativistic speeds, which would explain their redshift through special relativity rather than cosmic expansion. Others proposed they might be windows into other universes or exotic new forms of matter. However, as more observations accumulated, a consensus began to emerge. The key breakthrough came with the realization that quasars might be powered by supermassive black holes at the centers of galaxies. This theory, revolutionary at the time, explained both their incredible luminosity and their compact size. The gravitational energy released by matter falling into a supermassive black hole could, in theory, generate the enormous amounts of energy observed. The discovery of quasars also had profound implications for our understanding of cosmic evolution. Their extreme distances meant we were seeing them as they existed billions of years ago, providing a window into the early universe. This revealed that quasars were much more common in the distant past, suggesting they represented a phase in galactic evolution rather than a separate class of objects. The revelation of quasars' true nature led to numerous other discoveries. Their bright, point-like nature made them perfect beacons for studying the intervening space between them and Earth. The absorption lines in their spectra revealed the presence and composition of intergalactic gas clouds, leading to our first detailed maps of matter distribution in the early universe. Today, more than half a century after Schmidt's discovery, quasars continue to play a crucial role in astronomy. They serve as cosmic lighthouses, allowing us to probe the most distant reaches of the observable universe. The study of quasars has become fundamental to our understanding of galaxy evolution, black hole physics, and the large-scale structure of the cosmos. What began as a puzzling observation of an unusual star has evolved into one of the most important tools in modern astronomy, demonstrating how a single discovery can revolutionize our understanding of the universe. To understand the true nature of quasars, we must delve deep into their anatomy, examining the incredible cosmic machinery that makes them the universe's brightest beacons. At their heart lies an intricate system of components working together to generate unprecedented amounts of energy. At the very center of every quasar sits its powerhouse, a supermassive black hole with a mass ranging from millions to billions of times that of our Sun. This cosmic giant acts as the gravitational engine that drives all of the quasar's processes. Unlike smaller black holes formed from collapsed stars, these behemoths are massive enough to maintain a stable accretion process while generating enormous amounts of energy without immediately consuming all nearby matter. Surrounding this central black hole is perhaps the most crucial component in a quasar's anatomy, the accretion disk. This is a flat, rotating disk of superheated gas and dust that spirals inward toward the black hole, much like water circling a drain. As matter in the accretion disk orbits closer to the black hole, it experiences extreme friction and compression, heating up to temperatures of hundreds of thousands or even millions of degrees. This intense heat causes the disk to glow brilliantly across multiple wavelengths of light, from X-rays to visible light to radio waves. The physics of the accretion disk is fascinating and complex. The disk's inner regions rotate at nearly the speed of light, while its outer edges move more slowly, creating differential rotation that generates intense magnetic fields. These magnetic fields play a crucial role in channeling some of the infalling matter and energy into another distinctive feature of quasars, their relativistic jets. These jets are among the most spectacular phenomena in the universe, narrow beams of particles and energy that shoot out from the quasar's poles at speeds approaching that of light. The jets can extend for hundreds of thousands or even millions of light years, far beyond the boundaries of their host galaxies. They're called relativistic jets because the particles within them move at such high speeds that relativistic effects become significant. These jets are responsible for the powerful radio emissions that first led to the discovery of quasars. The process of energy emission in a quasar is a remarkable demonstration of nature's efficiency. As matter falls toward the black hole, about 10% of its mass is converted directly into energy, a process far more efficient than nuclear fusion in stars, which converts only about 0.7% of mass into energy. This efficiency explains how quasars can produce such enormous amounts of energy from a relatively modest supply of matter. The energy emission occurs through several mechanisms working in concert. The accretion disk produces thermal radiation across the electromagnetic spectrum, with different regions of the disk emitting different wavelengths of light. The innermost regions, being hottest, produce X-rays, while outer regions emit visible light and infrared radiation. The relativistic jets generate synchrotron radiation as electrons spiral around magnetic field lines, producing the characteristic radio emissions. Another fascinating aspect of quasar anatomy is the broad line region, an area of fast-moving gas clouds above and below the accretion disk. These clouds, illuminated and heated by radiation from the accretion disk, produce the distinctive broad emission lines seen in quasar spectra. Further out lies the narrow line region, where gas moves more slowly but still contributes to the quasar's spectral signature. The entire system is surrounded by a thick torus of dust and gas that can obscure our view of the central regions depending on our viewing angle. This dusty torus is crucial to our understanding of different types of active galactic nuclei, as it explains why similar objects can appear different depending on our perspective. All these components work together in a cosmic dance of extreme physics. The supermassive black hole's intense gravitational field pulls in matter. The accretion disk heats and processes this matter while generating intense radiation. Magnetic fields channel some of this energy into powerful jets, and surrounding regions of gas and dust interact with the radiation to produce distinctive spectral signatures. Understanding this complex anatomy has been crucial in explaining not just how quasars work, but also their role in galactic evolution. The enormous energy output from quasars can significantly influence their host galaxies, regulating star formation and contributing to the evolution of the entire galaxy. The study of quasar anatomy continues to provide new insights into extreme physics, helping us understand how matter behaves under conditions impossible to replicate on Earth. The mechanism behind a quasar's extraordinary brightness represents one of the most efficient energy-producing processes ever discovered in the universe. Let's explore the fascinating details of how these cosmic powerhouses generate their incredible luminosity. The accretion process stands at the heart of a quasar's brilliance. As matter falls toward the central supermassive black hole, it doesn't simply plunge straight in. Instead, it forms a rotating disk of gas and dust, much like water swirling around a drain. This process is governed by the conservation of angular momentum, causing the infalling material to orbit the black hole in increasingly tighter circles. As this matter spirals inward, several crucial physical processes occur simultaneously. The extraordinary energy efficiency of a quasar comes from its ability to convert matter directly into energy with unprecedented efficiency. While nuclear fusion in stars converts only about 0.7% of mass into energy, the accretion process in quasars achieves an astounding efficiency of up to 40% in theory, though typical values are closer to 10%. This means that for every kilogram of matter falling into the black hole, up to 400 grams are converted purely into energy, following Einstein's famous equation EmC2. This extraordinary efficiency explains how quasars can outshine entire galaxies while consuming relatively modest amounts of matter. The temperature in a quasar's accretion disk reaches mind-boggling levels. As matter spirals inward, several heating mechanisms come into play. Friction between different layers of the disk, compression of the infalling material, and the intense gravitational forces all contribute to heating the disk to temperatures ranging from tens of thousands to millions of degrees Kelvin. The inner regions of the disk, closest to the black hole, experience the most extreme temperatures, while the outer regions remain relatively cooler. One of the most fascinating aspects of quasars is their emission across multiple wavelengths of the electromagnetic spectrum. Different regions of the accretion disk, at different temperatures, emit radiation at different wavelengths. The hottest inner regions primarily emit X-rays and ultraviolet radiation. The middle regions produce visible light, while the cooler outer regions emit infrared radiation. Additionally, the powerful magnetic fields in the disk and jets cause charged particles to emit synchrotron radiation, producing strong radio waves. This multi-wavelength emission makes quasars visible across the entire electromagnetic spectrum, from radio waves to gamma rays. The intense radiation pressure generated by this process actually helps regulate the accretion rate. If too much matter tries to fall in at once, the resulting radiation pressure pushes some of it away, creating a self-regulating system. This feedback mechanism helps explain why quasars can maintain their incredible brightness for millions of years without quickly consuming all available fuel. If you're amazed by the power of quasars, don't forget to leave a like and share your thoughts in the comments. What do you think would happen if a quasar suddenly appeared near the Milky Way? Consider how its intense radiation and powerful jets might affect our galaxy and life on Earth. Would its gravitational influence reshape our cosmic neighborhood? Share your speculations and let's discuss this fascinating cosmic scenario together. This remarkable energy-generating mechanism continues to be a subject of intense study. Modern observations and computer simulations are helping us understand the complex interplay between gravity, radiation, and magnetic fields that makes quasars the universe's most efficient natural power plants. Their study not only helps us understand these extreme objects, but also provides insights into fundamental physics under conditions we could never recreate on Earth. In the realm of cosmic extremes, quasars consistently push the boundaries of what we thought possible in the universe. Let's explore some of the most extraordinary examples ever discovered, breaking down their record-breaking characteristics and mind-bending statistics. The brightest known quasar, designated as SMSS J215728.21 360215.1, shines with a luminosity of over 500 trillion times that of our Sun. This cosmic beacon, discovered in 2019, is so bright that if it were placed at the center of our Milky Way, it would outshine the full moon by a factor of thousands, and would be visible even in broad daylight from Earth. Its incredible brightness comes from a supermassive black hole consuming matter equivalent to about 1,000 Earth masses every day. When it comes to distance records, we find quasar J0313 1806, which currently holds the title for the most distant quasar ever observed. This ancient cosmic lighthouse is seen as it appeared 13.03 billion years ago, just 670 million years after the Big Bang. What makes this discovery particularly remarkable is that it harbors a supermassive black hole with a mass of about 1.6 billion solar masses. Its existence so early in the universe's history challenges our theories about how such massive black holes could form in such a relatively short time after the Big Bang. The most massive quasar discovered thus far is TON 618, which harbors a truly monster black hole, estimated to be 66 billion times the mass of our Sun. To put this into perspective, this single black hole has a mass equivalent to about 170 million times the mass of all the stars in our Milky Way's central bulge combined. The sheer scale of this object challenges our understanding of how such enormous black holes could form and grow. The comparisons between these extreme quasars and more familiar cosmic objects are truly staggering. Consider these mind-bending facts. A single one of these ultra-bright quasars can outshine all the stars in 1,000 normal galaxies combined. The energy output of the brightest quasars in a single second exceeds what our Sun will produce in its entire 10 billion-year lifetime. The gravitational pull at the edge of their supermassive black holes is so intense that matter orbits at speeds approaching 99% of the speed of light. The accretion disks around these monster quasars can reach temperatures of millions of degrees Celsius, far hotter than the surface of even the hottest known stars. Their relativistic jets can stretch across millions of light-years, spanning distances greater than 100 times the diameter of our entire Milky Way galaxy. To comprehend the true scale of these objects, consider that the light we observe from the most distant quasars has been traveling through space for over 13 billion years. This means we're seeing these objects as they existed when the universe was less than 5% of its current age. The fact that we can detect them at all from such vast distances is a testament to their incredible power output. The energy efficiency of these extreme quasars is unmatched in nature. While nuclear fusion in stars converts about 0.7% of mass into energy, these most extreme quasars can achieve efficiency rates of up to 40% in converting matter to energy. This means they are the most efficient natural engines in the known universe. Their supermassive black holes are so large that if placed in our solar system, they would engulf not just the orbit of Earth, but would extend beyond the orbit of Neptune. The gravitational field around these objects is so intense that time itself flows noticeably slower in their vicinity, a demonstration of Einstein's theory of general relativity at its most extreme. These record-breaking quasars continue to challenge our understanding of physics and astronomy. Each new discovery pushes the boundaries of what we thought possible in the universe and forces us to revise our theories about how such extreme objects can form and evolve. They serve as cosmic laboratories for testing our theories of gravity, radiation, and matter under conditions we could never hope to recreate on Earth. The energy output of a single quasar is one of the most astonishing facts in all of astronomy. When we say that one quasar can emit more energy than 100 galaxies combined, we're actually being conservative in many cases. Consider that a typical galaxy contains hundreds of billions of stars, and yet a single quasar's energy output can dwarf them all. To put this in perspective, imagine all the energy emitted by the roughly 200 billion stars in our Milky Way, multiply that by 100, and you're still not matching the power output of some of the most energetic quasars. This incredible energy output is sustained by consuming matter equivalent to several hundred Earth masses every year. The accretion disk temperatures in quasars reach levels that are difficult to comprehend. While the surface of our Sun is approximately 5,500 degrees Celsius, the accretion disks in quasars can reach temperatures of millions of degrees. This extreme heat is generated by several processes, including intense friction as matter spirals inward, compression of the infalling material, and the tremendous gravitational forces at play. These temperatures are so high that the material in the disk is transformed into a state of matter called plasma, where electrons are stripped from their atoms. The intense heat causes the disk to emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. One of the most puzzling aspects of quasars is their variable brightness. Some quasars can significantly change their luminosity over periods as short as a few days or even hours. This rapid variability provides crucial information about their size because, according to Einstein's theory of relativity, no object can change its brightness faster than the time it takes light to travel across it. Therefore, if a quasar's brightness changes in just a few days, its light-emitting region must be smaller than a few light days across. This is remarkably compact for an object producing such enormous amounts of energy, and it helped astronomers confirm that supermassive black holes must be powering these cosmic beacons. Perhaps the most mind-bending aspect of quasars is the incredible speeds achieved by matter in their accretion disks. As material spirals closer to the black hole, it accelerates to velocities approaching 99% of the speed of light. At these relativistic speeds, Einstein's special relativity becomes crucial for understanding the physics involved. Time dilation effects become significant, meaning that time actually flows more slowly for this rapidly moving matter compared to our reference frame on Earth. The material experiences intense effects of special relativity, including length contraction and mass increase. These extreme conditions create a natural laboratory for testing fundamental physics in ways impossible to replicate on Earth. The most powerful quasars can emit energy equivalent to the conversion of several thousand Earth masses into pure energy every year. The magnetic fields around quasars can be millions of times stronger than Earth's magnetic field. Some quasars shoot out jets of particles that extend for millions of light years, longer than many galaxies are wide. The light from distant quasars has been traveling so long that we see them as they existed billions of years ago, providing a window into the early universe. The supermassive black holes powering quasars can be so large that they could encompass the orbits of all planets in our solar system. Understanding these extreme properties of quasars has revolutionized our understanding of physics and the universe. They serve as cosmic laboratories, where we can observe matter and energy behaving under conditions far more extreme than anything we could create on Earth. Their study continues to provide new insights into fundamental physics, the evolution of galaxies, and the nature of space and time itself. These remarkable objects remind us that the universe is capable of creating phenomena far more extreme than anything we might have imagined, pushing the boundaries of our scientific understanding and revealing new mysteries for future generations of astronomers to explore. Leading experts in the field of quasar research have provided fascinating insights into these cosmic phenomena, helping us understand their nature and evolution. Let's explore their perspectives and the latest research developments. Sir Roger Penrose, Nobel laureate in physics, has made significant contributions to our understanding of black holes and quasars. He famously stated that supermassive black holes at the heart of quasars represent nature's most perfect machinery for converting matter into energy. Penrose's work on the mathematics of black holes helped explain how these objects can be so efficient at generating energy. His singularity theorems demonstrated that the formation of black holes is not just possible, but inevitable under certain conditions in the universe, providing a theoretical foundation for understanding how quasars' central engines form. The Event Horizon Telescope collaboration has revolutionized our understanding of supermassive black holes, and by extension, quasars. Their groundbreaking work has provided the first direct images of black hole shadows, including the famous image of M87's supermassive black hole. Current EHT research is focusing on studying the complex dynamics of material around supermassive black holes, providing unprecedented insights into how quasars' accretion disks and jets function. The team is working on capturing more detailed images of these systems, which could help resolve long-standing questions about how relativistic jets form and evolve. One of the most heated debates in modern astrophysics concerns the formation of primordial quasars. Dr. Priyamvada Natarajan, a leading expert in this field, points out that the discovery of extremely massive quasars in the very early universe poses a significant challenge to our current theories. How did these objects accumulate so much mass so quickly? Some researchers propose that the first black holes formed directly from the collapse of massive gas clouds in the early universe, bypassing the usual stellar evolution process. Others suggest that early black holes merged rapidly or grew through periods of super-Eddington accretion. Looking to the future, experts predict fascinating developments in quasar evolution. Dr. Neil deGrasse Tyson has noted that as the universe continues to expand and galaxies consume their available gas, quasars will become increasingly rare. Many astronomers believe we're already past the peak era of quasar activity, which occurred when the universe was about 3 billion years old. Future predictions suggest that while individual quasars might still form, their overall numbers will continue to decline as the universe ages. Take a moment to ponder this mind-bending question. How many galaxies in the observable universe do you think are brighter than a single quasar? The answer might surprise you: virtually none. Even the brightest galaxies we know of cannot match the energy output of a typical quasar. In fact, a single powerful quasar can outshine hundreds or even thousands of galaxies combined. This fact alone helps us appreciate the extraordinary nature of these cosmic powerhouses. Current research by the James Webb Space Telescope team is adding new dimensions to our understanding of early quasars. Dr. Jane Rigby, one of the project's leading scientists, suggests that we may soon discover even more distant and powerful quasars than previously thought possible. These observations could revolutionize our understanding of how the first supermassive black holes formed and evolved in the early universe. The scientific community continues to debate and investigate several key questions about quasars. How do supermassive black holes grow so quickly in the early universe? What role do quasars play in regulating galaxy formation and evolution? How do the most powerful jets form and maintain their coherence over millions of light years? What is the connection between quasar activity and star formation in host galaxies? As our observational capabilities continue to improve with new telescopes and technologies, experts anticipate that we will uncover even more surprises about these fascinating cosmic objects, potentially revolutionizing our understanding of the early universe and the fundamental laws of physics that govern it. The relationship between quasars and galactic evolution represents one of the most profound discoveries in modern astronomy. These cosmic titans don't merely exist within galaxies. They actively shape the destiny of their galactic hosts in ways that astronomers are only now beginning to fully comprehend. At the height of their activity, quasars unleash powerful winds and radiation that can profoundly influence star formation across their entire host galaxies, effectively determining the galaxy's ultimate fate and structure. In the early universe, quasars played an even more crucial role than previously imagined. Recent observations reveal that these cosmic powerhouses acted as celestial sculptors, helping to shape the very structure of the cosmic web we observe today. During the universe's first billion years, quasars produced powerful outflows that distributed heavy elements throughout intergalactic space, enriching the pristine cosmos with the building blocks necessary for future generations of stars and planets. Their intense radiation also helped ionize the neutral hydrogen that pervaded the early universe, contributing to a profound transformation known as cosmic reionization. The fate of quasars themselves tells an equally fascinating story. As these cosmic engines consume their surrounding matter, they gradually exhaust their fuel supply. Many once brilliant quasars have now faded into relative obscurity, leaving behind dormant supermassive black holes at the centers of galaxies, including our own Milky Way. This transition isn't merely an end, but represents a natural evolution in the life cycle of galaxies. Modern observations suggest that most large galaxies went through a quasar phase early in their history, making these objects crucial chapters in the cosmic story rather than mere astronomical curiosities. What makes this revelation particularly compelling is the discovery that quasars may experience multiple active phases throughout a galaxy's lifetime. When new gas becomes available, perhaps through galactic mergers or cosmic gas streams, dormant supermassive black holes can reignite, temporarily resuming their quasar activity. This cyclical nature suggests that even apparently quiet galaxies might harbor sleeping giants that could awaken under the right conditions. Looking toward the far future, astronomers predict a gradual decline in quasar activity across the universe. As galaxies gradually exhaust their gas supplies and the universe continues its expansion, new quasar formation will become increasingly rare. The last quasars might finally flicker out trillions of years from now, marking the end of an era that helped shape our universe's evolution. However, their legacy will persist in the structure and composition of galaxies, the distribution of heavy elements throughout space, and our understanding of the most extreme phenomena in the cosmos. This deeper understanding of quasars' role in cosmic evolution has profound implications for our place in the universe. Every galaxy, including our own, bears the influence of these ancient cosmic engines. The heavy elements in our planets, in our bodies, and in everything around us were partly forged and distributed by the intense processes occurring around quasars in the early universe. In this way, these distant cosmic beacons are intimately connected to our own existence, making their study not just an exploration of extreme physics, but a journey to understand our own cosmic origins. The human context of quasar research reveals how these distant cosmic beacons have become essential tools in our quest to understand our place in the universe. Their study represents far more than abstract astronomical research. It provides crucial insights into our cosmic origins and future. Quasars serve as irreplaceable cosmic chronometers in our efforts to understand the universe's history. Because their light travels across billions of light years to reach us, they provide direct windows into different epochs of cosmic evolution. When we observe a quasar 10 billion light years away, we're seeing the universe as it existed 10 billion years ago, providing crucial data about conditions during that era. This temporal insight helps astronomers piece together the universe's developmental timeline, much like archaeologists use artifacts to reconstruct human history. The practical applications of quasar research extend into unexpected areas. Their intense brightness makes them perfect reference points for measuring cosmic distances and mapping the universe's structure. Astronomers use them as cosmic lighthouses, illuminating the vast seas of space between galaxies. As their light travels through space, it passes through countless clouds of gas and dust, leaving distinctive absorption patterns in their spectra. These patterns create a cosmic roadmap, revealing the distribution and composition of matter throughout the universe. This mapping capability has revolutionized our understanding of cosmic structure. By studying hundreds of thousands of quasars, astronomers have constructed three-dimensional maps of the universe's large-scale structure, revealing a cosmic web of galaxies and dark matter that spans billions of light years. These maps help confirm and refine our cosmological models, providing crucial tests of theories about dark matter, dark energy, and the universe's expansion. The future of quasar research stands on the brink of transformation with the advent of new telescopes and technologies. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is already revealing previously invisible aspects of distant quasars. Its observations are helping us understand how the first supermassive black holes formed and grew in the early universe, potentially revolutionizing our understanding of cosmic evolution. Looking ahead, the Vera C. Rubin Observatory, set to begin operation soon, will conduct the most comprehensive survey of the night sky ever attempted. Its legacy, survey of space and time, is expected to discover millions of new quasars, dramatically expanding our sample size and enabling statistical studies that were previously impossible. This wealth of data will help answer fundamental questions about quasar evolution and their role in shaping galaxies. Perhaps most excitingly, the next generation of gravitational wave detectors promises to reveal new aspects of quasar physics. These instruments will be able to detect the gravitational waves produced when supermassive black holes merge, events that often trigger quasar activity. This will provide a completely new way to study these cosmic phenomena, complementing traditional electromagnetic observations. The human implications of this research extend beyond pure science. Understanding quasars helps us grasp our cosmic context, how galaxies form, evolve, and create the conditions necessary for life. The heavy elements essential for life on Earth were partly distributed through space by ancient quasar activity. In this way, our very existence is connected to these cosmic powerhouses. Moreover, quasar research drives technological innovation. The challenges of observing these distant objects have spurred the development of more sensitive detectors, more powerful computers, and more sophisticated analysis techniques. These advances often find applications in other fields, from medical imaging to data science. For the next generation of astronomers, quasars will continue to provide exciting research opportunities. The combination of new observatories, improved computational capabilities, and novel theoretical approaches promises to unlock more secrets about these fascinating objects. Students entering the field today might help discover how the first supermassive black holes formed, understand the physics of relativistic jets, or reveal new connections between quasars and galaxy evolution. This research also raises profound philosophical questions about our place in the cosmos. Studying objects that existed billions of years ago, yet influence our understanding of the present universe, challenges our perception of time and causality. It reminds us that we are part of a vast, interconnected cosmic story that began long before our species existed and will continue long after. As we look to the future, quasar research stands as a testament to human curiosity and ingenuity. From their mysterious discovery to our current sophisticated understanding, these cosmic beacons continue to illuminate not just the distant universe, but also the path of human scientific progress. They remain powerful reminders of how much we've learned about the cosmos and how much more there is still to discover. Quasars represent far more than mere cosmic beacons illuminating the darkest corners of our universe. As we've explored throughout this journey, these extraordinary objects serve as invaluable windows into the cosmic past and natural laboratories that push the boundaries of known physics. Their role as cosmic time machines cannot be overstated. When we observe distant quasars, we're looking back billions of years, witnessing the universe as it existed during its youth. These observations have revolutionized our understanding of cosmic evolution, revealing how galaxies formed and grew in the early universe. The most distant quasars show us a universe barely 670 million years old, providing crucial insights into the cosmic dawn when the first massive structures began to emerge from the primordial darkness. As natural laboratories, quasars present us with physical conditions impossible to replicate on Earth. They're extreme environments where matter approaches the speed of light, where temperatures soar to millions of degrees, and where gravitational forces stretch the fabric of space-time itself, allow us to test fundamental theories of physics. Einstein's theories of special and general relativity face their most stringent tests in the violent vicinity of quasars, while quantum mechanics grapples with explaining the behavior of matter under such extreme conditions. Looking ahead, quasars will continue to play a pivotal role in advancing our cosmic understanding. Next-generation telescopes and instruments will reveal ever more distant quasars, pushing back our view of the cosmic frontier. Advanced computer simulations will help us better understand the complex physics driving these remarkable objects, while new theoretical work may finally resolve the puzzle of how supermassive black holes formed so quickly in the early universe. Don't miss out on our upcoming explorations of the cosmos. Subscribe to Exploring the Universe and hit the notification bell to stay updated on our latest videos about the universe's mysteries. Show your support by leaving a like, sharing with fellow astronomy enthusiasts, and following us on social media for more fascinating astronomical content. Join our growing community of cosmic explorers as we continue to unravel the secrets of the universe together. Remember, every like and share helps spread the wonder of astronomy to more curious minds across the globe.